All right. So this is the asynchronous class. We're going to try to make our way through hypothesis testing, at least, to introduce the basic idea. What we're doing in this class is really setting up the sort of standard way of doing hypothesis testing with a t-test. So we're going to do a one sample t-test, build up the intuition for what we're doing, and then we're actually going to implement it in code. So that's what we're doing today. And then in the next couple of classes, we're going to start working with regression, which is just a sort of more general approach to the thing we're doing in this class. So we're going to, where we left off last time, we started thinking about confidence intervals. So we had the big question last time, which was that, from the central limit theorem, we found that x bar follows a normal distribution around the truth. So then sort of what do we do with that? We tried to systematize this distribution of x bar around the truth, essentially the closeness of x bar and mu. We had this idea of a sampling distribution with a sampling error. So if we know sigma and we know the truth, we know that the distribution of the sample mean will follow this distribution around the truth. So the standard error gives us the variability in the sample mean, which we said was less variable than the sampling distribution itself. So we talked about some of the intuition for where this standard error comes from. We said, when we sum a bunch of samples, the variances sum themselves. So if we take two samples like this, this is just an identity. The variance of A plus B is equal to the variance of B plus the variance of A. So when we do that n times, then we just get n times the variance for any one of them. Then when we divide it by n, it turns out by the identities of variance, this gives us n squared. So n variances gives us n squared. So when we do this for when we're trying to find the mean, we have to divide the sum by n, which means we have to divide this thing by n squared. So that gives us sigma squared over n, because one of the n's cancels. And so we walked through, so the standard error is just the square root of the variance. We talked about confidence intervals if we know sigma. So we said we can calculate any probabilities we want because we know the approximate distribution of the sample mean. So we can calculate anything under the curve, just like we do with normal distributions. If we have the distribution itself, we can just calculate probabilities. So if we're looking at all of the samples that would fall within one standard deviation of the mean, this is something we can just compute directly. And this is actually something we did. So we would know, after we computed it, that within one standard error of the mean, we would have 68% of the data. So if we just randomly draw x bar from whatever distribution produces it, we know that will fall within one standard error of the truth 68% of the time, which is amazing that we have the ability to be able to do this. This is what we call a confidence interval. But you'll remember we had two things that were unknown to us. First was the center, and then second was sigma. We don't actually ever observe these things ever, or at least generally in practice. So to get around one of these problems, we said there were two perspectives, and both are mathematically equivalent. So the first is we can think about the standard interpretation of the central limit theorem, which is that x bar follows a distribution around mu. So mu is known to us for certain. And so when we sample, we're actually just constructing a distribution of x bars around mu. But mathematically identically, we can think of the distribution given to us by the central limit theorem as actually a distribution of how kind of close mu is to the sample that we drew. So the sample mean x bar. So instead of centering the distribution on the truth, we're actually just moving the distribution to be centered on x bar. And these two things are mathematically identical because what the central limit theorem is actually telling us is about the closeness between the two. Nice. And so we walked through this picture that no one seems to like, which is that we have a bunch of samples. Each one of the samples, I've constructed a confidence interval around the mean, and then each one of these points represents the sample mean. So every time we draw, there's some random variability in the sampling error, which means some of the time the sample mean will actually fall outside the 95% confidence interval constructed around the truth. And so you can see we actually, even with a very high level of confidence, we have a lot of data that's falling outside the 95% confidence interval. But what we did, the amazing thing, is that we shifted the focus from centering the confidence interval around the truth to centering it around the sample mean. And so when we did that, because the sample mean is the thing that has the variability in it, there's no variability in the truth. What this means is that the 95% confidence interval is now moving around with the sample mean. But the amazing thing is that mathematically, every time we get one of these misses, where the x bar falls outside the confidence interval constructed around the truth, mathematically, it must be true that that the mean is not within the confidence interval centered around the sample mean. And what this means is we don't actually need to know mu to construct the confidence interval. So we're just going to center the confidence interval around the sample mean. And I made a mistake in the slides here. This should be sigma. So we know sigma to be 1.6. We have a sample mean of 102.3. And then we walked through this example. We found the probability that mu is closer than 0.1 to x bar. So we're looking at the area under the curve between 0.1 and negative 0.1 and positive 0.1 around x bar. And so we did that using this code here, which just gave us the area under the curve between those two numbers. And then we asked us sort of the reverse question, which is, what's the 95% confidence interval? So if we wanted the area under the curve to give us 95%, what are those two bounds? So this code gave us the confidence interval. The problem, though, was that we don't know sigma either. We don't know mu, and we don't know sigma. Those are both population parameters, and we never see the population. So what we said in that case was that we, just like we used x bar to estimate mu, we're going to use the sample standard deviation to estimate sigma. But to do this, we have to think a little more deeply about the variability here. S is a sample statistic, which means there's sampling error with S, like there is with x bar. And so what I've done here is I've actually just run a bunch of samples and then plotted the histogram of the sample standard deviation. So the standard deviation tells us the variability in the sample. This tells us the variability in the variability of the sample. So it's sort of one level higher. So the variability in the sample varies. So what this means is we can't just perfectly replace S in for sigma because by doing that, we're introducing more error. So what we did instead is I didn't derive this, but by introducing S, we actually introduce more variability. So we have to introduce sort of a new random variable that accounts for this additional variability. And the distribution that does this is the t-distribution, which this isn't an empirical regularity. This is actually a mathematical result. So there's, we're not taking this from, a simulation. This is actually from the math itself. We get a t-distribution, which we talked about if there's not much data, so few degrees of freedom, we get, thicker tails. So there's more weight in the tails. So we're less confident in our predictions. Extreme events happen more often. But as we increase the sample size, we go from 2 to 6. We go from this red line to this green line, and we get closer and closer to a normal distribution. So introducing S in for sigma, all it does is introduce more uncertainty, more weight on the extreme values. So heavier tails, and the t-distribution gets closer to normal as our sample size goes up, which is amazing. Okay, so what this means in total is X bar we can think of as following a normal distribution around the truth. We can center this distribution on the truth. So this normal distribution around the truth, we can actually just center that distribution on X bar because it's mathematically identical. We're essentially just thinking about the closeness of X bar and mu. And then when we replace sigma with S, we're adding some additional uncertainty, which we can then just calculate, or someone calculated the t-distribution, which is sort of we're adding in sort of the ratio of two random variables to give us the t-distribution. And then from here, we can then use the t-distribution to make claims about the truth. Okay, and so we're going to walk through this example. We didn't have time to do this in class, so I'm going to do this here, and then we're going to get into 3.4, which is actually using this to make claims about hypotheses. All right, so let's before we do hypothesis testing, I'm actually just going to run this at the top. So let's construct a sample. So we're going to have this sample. We have to run our imports first. And we're going to construct this sample. And this is the sample we've been using in our slide so far. So this is a random normal distribution centered around 12 with a standard deviation of 2.5. So our mean is, let's call this mu, is equal to 12. And then our sigma is equal to 2.5. And then we'll just plug these in. So mu, sigma, and n will make this equal to 30. Okay, so we're going to construct our sample. And this is just random data. We've collected this very similar to what you've done in your homework. So then what we're going to do next is calculate the sample statistics. So I'm just going to copy this over. So our X bar is just the mean of the sample. S is just the sample standard deviation. So we have this here. So NP standard deviation. And let me just see if this runs. Yeah, we'll take the degrees of freedom out. N is just the length of the sample. So it's the same N as we've calculated here. And then the standard error is just S divided by the square root of N. So I'll just run all these things. And then what we're going to do is actually calculate the sort of the T critical region. So how many standard deviations away from X bar is the two bounds that can contain 95% of the data. And so all we'll do here is just place this in. So this is the statistics module, so we have to actually import this. And then we're going to use the t distribution. And then PPF is just a way of sort of backing out the critical regions. All right, and so this is one of the, because we have two tails, we're looking at sort of both ends, we need 97.5 to make sure the alphas add up to 1. Sorry, alphas add up to 0.5. So we'll run this, and this gives us the critical regions on either side. So this is sort of how many standard errors away from X bar under the t distribution contains 95% of the data. Okay, so this is just an example. We can also calculate the confidence intervals from this critical value. So the last thing we'll do here is actually just calculate the confidence intervals. So we have this margin on either side of X bar. We have the number of standard errors that our critical region, how far away from X bar is our critical region. And then we multiply it by the standard error. So it's like how many standard errors on both sides of X bar contains 95% of the data. Okay, so then we'll just run this, and this gives us our 95% confidence interval. So we're saying between these two numbers, we are 95% confident. If we ran this a bunch of times, this approach will include the truth 95% of the time. All right, so this is a lot. We have a lot of stuff going on here, but the intuition is exactly as we've developed it. We look for, we're going to center the distribution from the central limit theorem around X bar. We don't see sigma, so we have to use S. But when we do that, we have to use the t distribution. And so we're looking for the critical region that on either side contains half of 5%. So if we were to run this thing with 0.25, this should give us the same number as this one, just negative. So these are our two critical regions, each tail containing half of the what's left over from the 95%, so 5%. All right, so you've seen these things before. You've worked with this in your stats class. What we're going to do next is actually use this to answer questions, which is what we do with hypothesis testing. So we're going to set up some of the ideas at the beginning, and then we're going to actually get into some hypotheses, and we're going to make some tests. All right, so just as a recap of what we just did, the central limit theorem gives us this systematized closeness of X bar and mu, which is really nice. And then we talked through the fact that we don't have to center that distribution on mu. We can actually center it on X bar. And then when we substitute S in for sigma, that introduces some extra variability, which then means we have to include extra variability in our distribution. So we use a t distribution because of that. If you want a more formal a derivation of where that comes from, we can talk about that in class or in office hours. But I'm not going to talk about it in class. It's not something that we sort of need to know for our purposes, except that it's there. And then we talked about the standard error. So as the sample size goes up, the distribution of the sample mean goes down. So larger samples have less variability, just like the rolling dice example. As we increase the number of dice, the probability of getting an average of 1 goes way down because it's just very difficult to get large samples with an average of 1. You have to have 1 on every dice in the sample. Okay, so the standard error is inversely related to the size of the sample. And then what we said is 95% of samples will be essentially no further away than, with large samples, no further away than 1.6 standard errors from U. And this is one particular level of confidence when we talked about samples, but we can do this really for any level of confidence. This is just a picture essentially of 95% confidence. We have the distribution centered on 0, and then we're just looking at how far away x bar is from sigma. Sorry, from mu. And so what we do is we construct these critical regions, these distances from the center of the distribution, where we can see data. And so what we're trying to do is just measure our level of confidence. How likely is an extreme event? Okay, so with our last example, we talked through where the true mean wait time is, simply observing the samples. But what we're trying to do with hypothesis testing, and essentially what we do in practice in general, is try to make specific claims. So we try to test a specific claim about the truth. In the past, what we've done is we've looked at a specific sample, and then we've checked how far away, or like what the probability of extreme events is. But what we're going to do here is ask a different type of question. We're going to essentially flip the question, which is, if my boss were to ask me specifically about a particular number, so you're thinking about wait times at your restaurant, and your boss asks you about wait times, it makes a claim that the wait time is 10 minutes. We can actually just very directly port over the confidence interval approach to thinking about this question. We have to do a little bit of work here at the front, but almost everything will look pretty familiar. Essentially, we're going to try to ask whether our data is consistent with 10 minutes being the average wait time. And what we're going to do is actually construct a distribution around this claim. So instead of looking at where mu might be, what we're doing is we're actually assuming that the claim is true, and then checking how likely it is that we would see something like our sample. Okay, so let's just walk through a bit of an example here. So let's say we see an average wait time of 10 minutes and 85, or 10.85 minutes. So because seconds don't go to 100, this isn't exactly seconds. Is this consistent with 10 minutes? So we can see that the sample mean doesn't exactly equal the guess. It's slightly larger. But because of sampling error, this is something we could expect. So like you see in your homework, you're not actually ever going to exactly match the truth with your sample. So there's a bunch of variability around the truth. So what we're going to do instead is simulate, this is sort of our kind of approach. We're going to simulate data where the truth is assumed to be 10. And then we're going to check how far away our observed mean is from that truth. And then this is going to allow us to talk about levels of confidence under this mean being true. So essentially, we're gonna ask how surprising our observed x bar would be if mu actually was 10 minutes. So that's going to be our question. Okay, so none of the math we're going to do here is going to look any different than what we did with confidence intervals. We're just going to approach it from a slightly different perspective. So, so here we're going to say we have so going back to our numbers, we have a mean assumed to be 10, and we have a sample standard deviation of 2.5. So we can just go through and calculate the sample standard error in this way. So I'm just going to copy this over. We'll work in our notebook. So we have some sample data here. We have the sample mean. We have the population mean that we're guessing. We'll talk about hypotheses a little bit later. But this is our guess. Then we have a sample standard deviation of 2.5. And then a sample size of 30. So we're going to run this. We can calculate the standard error just by the equation that we use. So this is, and we derived, right? We have the sample standard error, the sample standard deviation, divided by the square root of the sample size. So we can just check what this is. And we can check that this actually matches the math we've done here. Okay, so this is the setup for the standard error. Then we're saying that the truth, our guess for the truth is equal to 10. So we're using the sample standard deviation, which means we have to use a t-distribution. This 29 here is what we call the degrees of freedom. It's essentially just one fewer than the sample size. So this tells us about our level of confidence. So remember, as the sample size gets larger, the variability in the sample actually goes down. And so the smaller the sample size, the more variability there is, added by the introduction of the sample standard deviation in for sigma. So when this number gets larger, we get closer and closer to a normal distribution. But for smaller samples like this, we have to specify the degrees of freedom. So then the t-distribution is centered on the guess here. So we've plotted the distribution, and we have a standard error. So this is the variability in the t-distribution itself around the guess. So we're saying we're going to assume that the guess is true. And we're going to say that X bar follows this distribution centered on 10. So this is a picture of the distribution here. We've centered the t-distribution on 10. And we can see that our X bar is pretty far in the scope of this distribution from 10. So, 10 and 10.85 are not actually that different. It's just because we have a pretty high level of confidence in our distribution, within the scope of the distribution, they look pretty far away from each other. So what we want is for, we first want to find the critical value, but then eventually we're going to try to find essentially where on the distribution our sample mean falls. So what this code here does is it actually gives us the critical region, which is how many standard deviations away from the guess is our sample mean. So I'm going to copy this over and we'll talk about what it means. So this is, let me just run this. So this is our what we're saying, we want 95% of the data to fall within this interval. We have our degrees of freedom, which in this case should be 29. It's not going to change very much once we're above 25 or so. And what we're saying is we're going to look at the statistics package, look at the t-distribution within that statistics package, and then construct the 95% confidence interval around around 0. And so what this does is it gives us the critical regions. So this is how many standard errors on either side of our guess will the 95% confidence interval be. So this number is this one here. So this is the level of confidence. Now, what I've done, looks like I didn't include the math here in the slides, but what I've done, let's do it in code here. So if I add 10, so what we're going to do is take this first number and add 10 to it, but we're going to multiply this by the standard error. So this gives us, how many standard errors gives us the 95% confidence interval. Then we multiply by the size of the standard error, and then we subtract that margin from 10. That gives us essentially 9.07. And then on the other side, all we're doing is adding the standard errors, the 2.04 standard errors on top of the 10, which will give us the other side of the distribution. So 10.93. So what we've done here is we're looking at the two places on the distribution that contain 95% of the data. So that's going to be this vertical line here, sort of where the purple region begins, and then this one here, where the purple region ends. So what we're saying is we've actually constructed this interval to contain 95% of the data, or 95% of the data if 10 were the truth. So this purple region contains 95% of the data if 10 were the truth. And so what we're saying, essentially, if the true mean were 10, and we wanted, we were sort of thinking about 95% of the data falling within this interval, it wouldn't be surprising that we would get an observed mean of 10.85. And another way of saying this is that it's not surprising, given our data, that the truth would be 10. And the reason is that our observed truth falls within our 95% confidence interval. So this is sort of essentially the same math as what we've done to construct confidence intervals. We just kind of flipped the logic. If we instead observed, 11.5, which would be sort of out here, that is outside the interval. So if we needed a level of confidence at 95, 11.5 would fall outside of that confidence interval. So in some sense, that would be kind of more surprising. So if you're sort of sitting here seeing this and thinking about like maybe a feeling of arbitrariness about 95, you're on the right track. We pick these numbers because we want to make sure that we're, pretty confident. It's like 95% of the time we make a correct claim. But we don't always use the same numbers. So what we're going to do actually is we're going to formalize a null hypothesis, and then we're going to find a sort of a different way of constructing a hypothesis test, giving us a more flexible approach. Okay, so the example we just ran through was a specific claim about wait times. So that would be what we call the null hypothesis. It's a specific claim that the wait time on average is 10 minutes. We call this the null hypothesis. We often denote this with a H subscript 0 for null. So in the example we just walked through, that was a wait time of 10 minutes. We also call the sort of the converse of the null hypothesis the alternative hypothesis. So this is either denoted with H subscript 1 or an H subscript A for alternative. It's sort of the world we live in if we reject the null hypothesis. So in this specific example, that's, that mu is not equal to 10. And essentially, the approach we're going to develop, building on the intuition of what we just did, was essentially how surprising would our data have been if the null hypothesis were true. And then think about what would need to be true to feel confident rejecting the null hypothesis. So the way we do this, and we're going to talk about some of the limitations here. This is an often misused technique, is what we call a p-value, which is essentially a way of quantifying the level of surprise that we get if our hypothesis were true. So we see the data, we have a null hypothesis. How surprising is our data given that null hypothesis to be true? So what we're going to do here is, the way we define a p-value is essentially just the probability that under the null hypothesis, we see something as extreme as our data or more extreme. So it's at least as extreme a sample as what we're seeing. So the probability of getting extreme events. So for our example, we have a null hypothesis of 10. Our observed sample mean is 10.85. So then the p-value essentially captures how likely it is to get x bar or greater, sort of x bar or further away than x bar from 10 if the true mean is actually 10. So it's sort of a way of measuring the extremeness beyond our sample. So it's essentially the extremeness of our sample or greater. Okay, so we're going to continue our example here. This is just a picture, essentially, of what a p-value captures, and you've almost certainly seen this before. So here we have an observed mean, and what we want is to be able to quantify the areas in the tails. So we see the observed mean. How likely is it under, so centering the distribution on the null hypothesis, what's the probability we see our observed mean or anything more extreme? And I made a mistake here. This should be, we'll actually fix this number in code in a second, but this is a little too small. Okay, so what's the probability we get an error as large as our observed mean if the null hypothesis is true? So what we're going to do is actually go to code and find this number. So I'm going to copy this code over and we'll talk about what this means. So let's clean this up a little bit. Let's calculate a p-value. And we'll write in calcu a confidence interval. All right. So here we're going to set up our p-value. So what we're doing first is we're going to look at the stats t module, and then we're going to find the CDF. So this, you'll remember, is everything up to a certain point under the curve. So what we're going to do is actually try to find the area of this tail first. And then we're just, because the t distribution is symmetric, we're just going to multiply by 2. So our null hypothesis in this case, our mu0, is 10. And then our x bar, I'm actually going to change the notation a little bit. Well, let's keep the same notation. X bar is equal to 10.85. And then look at that, Gemini predicts what we're doing. So we have our sample standard deviation, we have our sample size, and then we have our standard error. And so all of that just goes into the CDF. So what we've done here, we're going to talk about what this actual thing is that we're constructing. This is essentially a t-value, which we'll talk about later. And then because the t distribution depends, like the weight of the tails depends on the sample size, we have to specify the degrees of freedom, which is, it's a little outside the scope of the sort of derivation of this class, like I've mentioned, but the degrees of freedom is the sample size minus 1. So when we run that, we get, a probability in one of the tails, this thing, that's equal to this number. Now we have 2 tails, so we have to multiply this by 2. So we get 0.072 or 73, which is slightly different than this number, which is fine. So this is a little too low. Our true p-value for for 10 is actually just roughly 7%. So the interpretation here is, if the truth were actually 10, we would see x bar or something more extreme than x bar 7.3% of the time. Okay, so often the way we interpret this is because the smaller that area is, the less likely it is for the null hypothesis to be true. So when we get a very small number, it means our guess is very far away from our observed x bar. So these two things are very far away when the p-values are very small. So we say that we reject the null hypothesis if the p-value is below some threshold. And these thresholds and the choice of our guesses, we're going to talk a lot about actually how we construct these things. It's often misused. We'll talk about how to misuse it so that you don't do it. We sort of have a problem at the moment in our journals about misuse of this result. But what the p-value tells us is this probability of errors based on the distribution centered around our null hypothesis. So often what we use is a p-value that's less than 5% to reject a claim. So here, because the p-value is greater than 5%, we would say that we don't reject it at a 5% confidence level. Okay, so this is how we construct a p-value. We don't have to check any tables. We have nice code that runs these things. So that's nice. So we get this thing without ever having to check a table. But I introduced this thing without actually talking about exactly what it was. We can sort of use this approach, but I want to spend some time talking about what we call t-statistics, which is a way of sort of standardizing our distributions in a way that makes thinking about the distribution easier to interpret. What a t-statistic does is it measures essentially how many standard errors the sample mean is from the null value. So we've talked about it in these terms before, but what we're going to do is construct a value that does it. And we can do all of these things without actually having to talk about t-statistics. So I'm saving it for the end so that we can get the intuition first. Because we have this equation that some people find, it's like there's so many equations running all over the place. We actually sort of don't need to work with this one directly, but we're going to talk about it. The t statistic measures essentially how many standard errors the sample mean is from the null value. So you'll see on top we have the difference, so the sort of closeness of x bar and our guess. And then on bottom we have our standard error. So this thing is like, on top is the mismatch, and then we ask how many standard errors is that mismatch. So if the standard error is 1 and the difference is 2, then we know that the x bar is 2 standard errors away from the guess. So our t-statistic would be 2 in that case, because there are 2 standard errors between x bar and mu. In our example, we have x bar is equal to this thing. We have our mu equal to 10, and then s is our sample standard deviation of 2.5. And then we have our sample size, so we can plug all these numbers in and play it out like this. Or we can just write some code. So what I'm going to do here is actually just write the code to compute the p-values using the t-stat, and actually just to compute the t-statistic directly. Okay, so let's just separate these things out. So this is our, all the stuff we've used before. And we can actually just write out the t-statistic. So this is all of the stuff we want. And then we're just going to copy over the t-statistic into this line. We have the sample mean minus the population mean. So this is like, the difference between what we see and then what we're guessing. And then on the bottom, we have the standard deviation divided by the square root of the sample size. So this is the standard error on bottom. So just like we talked about, we're actually just measuring the number of standard errors the sample mean is away from the population mean, or the null hypothesis. And so in this case, we end up having a t-statistic of 1.86, which you'll notice. So our standard error, s over the square root of n. And then let's take the difference. So we have a difference that's equal to this thing, and then we have a standard error that's equal to this thing. And you can see the difference is roughly twice the standard error. It's a little bit less than twice. And so what the t-statistic is doing is essentially just measuring how many standard deviations is the difference between the population mean and the sample mean. So that's kind of the intuition for what the t-statistic is doing. And you'll notice that we've actually already used it in the CDF for the t. This is, we have the difference on top, and then we're dividing it by the standard error. So this is awfully nice. And then the last thing we're going to do is calculate the p-value using the t-statistic. So you can either just compute it directly, or if you have the t-statistic, we can just calculate the p-value. So here we have the p-value. We want, well, let's talk through the details here. So this first part, sort of like the main part, is something we used above. This is finding how, where in the t-distribution the t-stat is. So we're putting an absolute value on it because, because we can look on either tail. So we're essentially we want to look at one of the tails versus the other. And if we put an absolute value on it, we're saying we're actually just going to look at this line here and then find everything below, which will give us, something that's close to 100%. So to find just the area of one tail, we take 1 minus this. So we're looking at the CDF gives us everything under the curve before we hit this bar. So if we take 1 minus that, we end up with what's in one of the tails. So this is one of the tails, but then we need to multiply this by 2, which is what we do down here. So this gives us a p-value, which is equal to 72. And this corresponds very nicely with what we did earlier. So we just used a different kind of approach to find the p-value. Okay, so we can use the t-statistic, or we can just compute the p-value directly. But either way we're doing it, what we're doing is finding the area that's more extreme than our sample, if the hypothesis were true. This is just an incredibly widely used tool. It's often misunderstood and is often misused. And so in this class, we're going to talk about some of the ways we misunderstand it. And in future classes, we're going to talk about how we can actually misuse it so that we don't. And some of the ways you can identify that is being misused. We use this not just for hypothesis testing with single means like this. We use it for testing differences between populations. We also use it in regression, which then allows us to do a lot of more intricate types of tests. So this is the foundation for all of those kinds of models. They are all variations on this. We check the error in the tails. Okay, so some cautions. We have what we call statistical significance, which is this level of probability of error. And then we also have practical significance. Sometimes we can reject a null hypothesis, which only tells us whether our result is due to chance or how likely it is due to chance. But it doesn't necessarily tell us that our result is meaningful in a sort of a real world context. We can find, because often we run models with very large sample sizes, we can actually find very tiny results, which may not have clear practical significance. So when we're thinking about these things, it doesn't, just because we have we're able to reject a null, doesn't necessarily mean that what we found is meaningful. It just tells us it's maybe it's unlikely due to chance. We can, find tiny differences with large samples. The main point here is we have to think about whether the magnitude is important and not just the p-value. And there's a lot of ways to misinterpret a p-value. The p-value is not the probability that the null hypothesis is true. The p-value assumes the null hypothesis is true and then calculates how surprising the sort of observed results are under that assumption. So a p-value of 0.04 doesn't mean that there's a 4% chance the null hypothesis is true. So it doesn't mean there's a 4% chance that it's something other than a 4% chance that the truth is 10 in our example. It's also not the probability that the results are due to chance. We have this really structured way of understanding the relationships between the variation we see in our data and in our models. The p-value it's not able to separate just randomness from so we have random variation, and then we have our real effects, and it's what this is telling us is not exactly that that the p-value is able to separate these things. The p-value of 0.4 doesn't mean that there's a 4% chance that our results are due to chance and 96% chance that they're real. This is not how you interpret it. It's also not the probability that the alternative hypothesis isn't true. It is true. The p-value doesn't. What we've done is we've constructed the null hypothesis, and then we've constructed a probability distribution under the assumption that the null hypothesis is true. And so we can't actually make claims about the probability that the alternative hypotheses are due to chance. So we're really only able to address this one hypothesis, the null. So we're not making claims about the alternative probabilities. Okay, the way we do interpret this, the reason we walk through all of this to arrive at a hypothesis testing procedure is because we sort of need to understand the procedure to understand what the thing is telling us. The way to interpret a p-value is as the probability of observing the test statistic or something more extreme under the assumption that the null hypothesis is true. So it's essentially like the compatibility between our data and our hypothesis. So the example I have written in the slides is, if we have a p-value of 0.04, it means under the assumption that the null hypothesis is true, we are going to see, just through random variation, our sample or something more extreme 4% of the time. So it's essentially how surprising our data is in the world of the null hypothesis. Okay, so this is the basic idea, and we're actually going to develop this core idea with many extensions. But this is the trunk that we're going to build the rest of the semester off of. So this is the statistic framework, which we're going to next time think about two different groups. So not just is our one sample 10 or not, but are these two samples different from each other? And then later what we're doing is building regression on top of this idea. So this is, I'm going to show you this a little bit later. This t-test approach is actually a very simple regression. So we're going to actually do all of this in the context of running regressions. They are exactly the same model, all under the same umbrella. We're also going to talk about ANOVA. So these are some of the things we're about to get to, which is essentially comparing between multiple groups. All right, so I think we'll leave this here. This is, I get excited about talking about these things. This is essentially how all of modern science takes data and turns it into models of how the world works. All right, so I'll see you in the next one.